Hello everyone. In last lecture itself I have started basics of fatigue life prediction. Today also I will discuss some more details about some more basics of fatigue life prediction. So, this is the content of today's lecture. Here I will discuss first endurance limit prediction using some approximate method, that is called approximate estimation of endurance limit. Then I will discuss about deterministic stress life problem, and I will also discuss some important aspects related to fatigue analysis, and here also I will discuss about knot sensitivity factor. So, first of all, endurance limit, how we can predict by some approximate estimation and why it is required. We know that laboratory determination of endurance strength is more precious and is laborious and time consuming types of job, because in last lecture itself I have discussed how to determine the endurance strength by laboratory test, that is RR Murray method, or you can say rotating beam machine approach. There how we can determine the endurance strength AC we have shown, and for a particular test itself you know that there can be required some days also. And also we observe that for getting this endurance strength we need lot of test result data. After that we plotted it in ascent curve, from there generally we can predict the endurance strength AC, that I have already told you. So, which is a laborious and time consuming job, and though it is precious, then also sometime this approximate estimation method also popularly using, and this method is also well standard method, that we can say. This experimental observation, a number of tests generally are required to prepare this ascent curve, which I have already told you, and each test consider a considerable time. It is therefore not possible to get that data regarding the fatigue properties of each and every types of material. So, for getting this data generally for each and every types of material is a tedious job, that you can say. For this reason, here whatever the procedure I am going to discuss, that we should follow. So, this is an approximate relationship between endurance strength and ultimate tensile strength of the material, this you can say. Now, you know by using generally tensile testing, you can easily predict what is the ultimate strength of a material, because for mild steel like stress versus strain, if you draw there, what we observe that it generally gives us a curve which looks like this. Now, here generally this is called yield stress, and this is generally called ultimate stress, or as it is the maximum value of this stress strain curve. That is why what happened, as it is a property of that material, you can say, that is why it is also called ultimate strength. Now, there is an generally approximate method we use to determine the endurance strength AC, which is correlating with this ultimate strength value, which is generally for mild steel types of material, steel material you can say, is considered as 0.5 into ultimate strength, whereas for cast iron generally it is generally this endurance strength you can related with ultimate strength. SUT means ultimate strength. So, this ultimate strength is 0.4 UT. Some other material like in case of aluminum, for wrought aluminum also I am just telling, wrought aluminum generally this value of endurance strength of for wrought aluminum, it is generally 0.4 of S ultimate of aluminum, and for you can say so for wrought aluminum you can say it is 0.4 into S ultimate, and for cast aluminum this AC dot generally is equal to 0.3 SUT. Okay. This is also some other material, this relation generally we use, because this aluminum and steel material have wide application in the field of industry or manufacturing industry, you can say. That is why we are discussing here steel mainly. Okay. Now, here one thing you should keep it in mind, whatever the AC dot we use, this AC dot generally the endurance strength, this AC dot is the endurance strength, here I have written for a rotating beam specimen subjected to reverse bending stress, this you should keep it in mind, AC dot. So, now you know in case of rotating beam specimen, we know this specimen is surface quality is a specimen standard is fully different than a commonly used engineering component. Like in engineering component, generally whatever the surface finish and other things will be there, that properties will be different than this rotating beam specimen. That is why here I have written AC dot, which I have shown here in case of steel and you can say cast iron, whatever the AC dot I have shown, that is generally endurance strength for rotating beam of specimen. That specimen is well surface finish, and that quality of this specimen follows some standard also. Now, there we can consider for other endurance strength, which I am representing by AC only. So, this AC represent the endurance limit stress for a particular mechanical component, which is again subjected to bending stress. What I am telling, understand. So, here one thing you should keep it in mind, this AC is different from this AC dot due to different number of factors. What are the different number of factors that I am going to discuss? Like AC dot the reliability 50%, but this particular mechanical component which can be subjected to some reliability which is little bit higher side or lower side. So, depending upon those value, generally what happens, this endurance AC is not, you can say, equal to AC dot. This you should keep it in mind. Now, what is the relationship between this actual or particular mechanical component endurance strength AC with this rotating beam specimen, considering some different factors? That relationship now I am going to discuss actually. Here one thing you should keep it in mind, generally for steel I have already told you SE dot is equal to 0.5 into S ultimate, correct. But this is valid for actually once the ultimate strength is less than equal to 1400 MPa. If the ultimate strength is more than 1400 MPa, then we should consider a constant value of endurance strength for rotating beam specimen. This you should keep it in, that value is half, or you can say 700 MPa, always this is a constant value. Okay. Now, we are going to discuss about what is the relationship between AC and AC dot, considering different factors. Now, that factor generally, what are the different factors, that is why here I have written. It has seen that the rotating beam specimen used in the laboratory for determination of the endurance limit is prepared very carefully and tested under very closely controlled condition. Whereas a normal you see mechanical component which is not subjected to these types of what it is called surface preparation, as well as it is not operated in very closely controlled condition. So, for that reason the differences are included by Joseph Marin, who identified some very important factors which generally quantified the effect of this surface condition, size of that mechanical specimen or mechanical component, which loading type, then effect of if it is subjected to some temperature effect, and some other factor also he considered, that is called miscellaneous item factor, or this is also sometimes called miscellaneous modifying factor. Considering all these different effect, he generally what it is called included some very important factor with this what it is called rotating beam specimen endurance strength, and he represent the endurance strength of a particular mechanical component, that means AC. So, as this relationship is established by Joseph Marin, that is why this equation name is called Marin equation. With this Marin equation can be represented like this. Here you can see, where this AC is equal to, you can say, K, KB, KC, KD, KE and KG with this endurance strength, that means endurance strength of a rotating beam specimen. So, with this AC dot he introduced these 6 different important factors. So, this each and every factor have its own importance in this and its own effect, you can say, in this AC. So, you know that AC dot equal to 0.5 into S ultimate for steel material, and for cast iron it is 0.4. So, you should keep it in mind. Now, you see what is this K? This K is called surface finish factor. I will discuss in details about each factor. KB is called size factor, KC is called reliability factor, KD is called temperature modifying factor, and this KE, whatever the KE is there, KE is called load factor. This load factor always you should keep it in mind. In case of reverse types of bending, this KE value is 1. In case of generally reverse axial load, this KE value is 0.85, and for completely reverse types of torsion generally this KE value is 0.59. This you should keep it in mind. For different types of fluctuating loading case, you can say, or reverse types of loading case, generally this KE value is varied. What I am telling, understand? Now, and this KG is a very important factor. This KG is called miscellaneous modifying factor. So, this KG generally is such a factor where we can include the stress concentration factors effect, because in case of welding generally this stress concentration or miscellaneous other modifying factors, like in case of welding, if there is occur some distortion, then due to this angular distortion, misalignment during welding process, whatever the effect will be there, those types of effect generally create some, you can say, stress concentration types of effect. So, that stress concentration types of effect we can include in this KG, which is called miscellaneous modifying factor. This you should keep it in mind. This is a very important factors. Generally in this factor we include the effect of welded joint in what is called endurance strength. This you should keep it in mind. Now, first of all I will discuss in details about the surface finish factor Ka. Now, surface finish factor generally you see it depends on, here I have shown, it depends on ultimate strength of the material, and it is also depends on what is called quality of surface finish. That means, it also depends on quality of surface finish. This you should keep it in mind. That is why what happens in case of rotating beam specimen generally which has very high polished surface and which is generally free from scratches, whereas generally a actual component which may not require that much of surface finish. That is why what happens there we can use different types of surface finish operation. Like this surface finish operation can be ground types of surface finish, it can be machine or cold drawn types of surface finish by using some lathe milling types of or other machining operation. It can be done by hot roll types of surface finish operation, as well as it will be done in as force types of what is called surface finish operation. For different types of surface finish operation, generally this surface finish factor is varying. So, for that generally what is called Sigley and Miss K, you can say, who suggested an exponential equation. This exponential equation generally is represented like this, that is A into S ultimate to the power B. This is an you can say exponential equation. This equation generally based on lot of experimental data points which is obtained by Knoll and Lifson. This you should keep it in mind. So, based on this data point for different types of surface finish operation, they generally establish this relationship. So, here one thing you should keep it in mind, if somehow this Ka is greater than 1, then what happens, always you should you need to consider Ka equal to 1. Okay. This you should keep it in mind, especially like in rotating beam specimen, the surface finish factor is considered as 1. What I am telling, understand? Now, here what this A, the exponential equation A and B, these two constant value is depends on what? This depends on type of what is called surface finish operation. Like for ground types of surface finish operation, this A value is 1.58 and B value is minus 0.085. Then for machine types of surface finish operation, here generally this A value is 4.51 and B value is minus 2.65. Similarly, hot rolled and what is called as force condition, whatever the value is there, that is generally given here. So, based on this two relationship, if we know this S ultimate value, then what happens, we can easily find out what is the Ka value. So, here generally this Ka equal to A to the power this exponential function, you can say, is represented in graphical manner. Here in this figure you can say surface finish factor from here itself you can say. Generally in case of polished types of surface like rotating beam specimen, they are generally this you see this surface finish factor is 1, I have already told you, which is used in rotating beam specimen. Now, in case of ground types of surface finish, its value is also is approximately within a range of 0.9, and always you should keep it in mind, whatever the different K, Kb, Kc, Kd and Kg factors I have shown, all has a value which is less than equal to 1. This you should keep it in mind. K should be less than equal to 1, Kb also should be less than equal to 1. What I am telling, and it should not greater than 1. Always you should keep it in mind. Its maximum value can be 1. It is varying from within a range of 1. This you should keep it in mind. It is not more than 1. Okay. So, never be confused these things. Okay. Now, in case of ground surface finish, its value is approximately 0.9. After that, you can say that in case of you see machine types or cold drawn types of case, generally if the ultimate strength, that is actually tensile strength, if this ultimate strength value is 400, that means if the ultimate strength is lower, then this surface finish factor is you see higher. If the ultimate strength is increased, because higher the value of ultimate strength, from this equation also you can say, because this B value is B value generally has a negative exponential. This you should keep it in mind. That is why what happens, higher the value of this ultimate strength, lower the surface finish factor value. From this generally curve also you can observe for different types of case, how the value is varying for steel material with different types of ultimate strength and different types of you can say surface finish type. Now, we will discuss about size factor. This size factor also has a significant effect you can say on endurance strength. Again I told you this size factor Kb also should less than equal to 1. In case of rotating beam specimen, its value is generally considered as 1. Now, what happened in case of actual mechanical component, this Kb value generally is less than 1. So, this size factor generally depends on size of the specimen which we are using for fatigue life or endurance strength calculation. So, this size factor generally higher the size of a specimen, generally there is a larger numbers of or greater number of surface defect can be there, because if the specimen is a small, then number of defect will be small in this specimen. If the specimen size will be higher, then only there is a chance of more you can say surface types of defect. So, for that reason generally what happens, depending upon the size of the specimen, for circular types of or cylindrical types of specimen, generally depending upon the diameter or cross sectional area of that specimen, generally for circular cross section this Kb value is generally given in this table. You can say, like if the diameter of a cylindrical specimen is less than 7.5 millimeter, then what happens, this Kb value is generally is equal to 1. That means, this size factor do not have any effect on endurance strength. Now, 7.5 to 50 millimeter thickness, this is in millimeter, this you should keep it in mind. This Kb value is generally 7.5 to 50 millimeter within range if the diameter is, here Kb value generally considered as 0.85, and if the d value is greater than 50, then you can consider this Kb value is 0.75. That means, higher the diameter of the cylindrical specimen, Kb value is for more decrease, you can say, because Kb value is less. Because if Kb value will be less, your endurance strength value, actual endurance strength value AC also will be less, because AC is depends on Ka, Kb, and generally here you can say AC dot. So, you see, so this K value, Kb value, it can be maximum 1, and if it is generally always less than 1, each and every value less than equal to generally 1, this you should keep it. Once it is less than equal to 1, that is why always this AC value is also less than, or it can be less than equal to AC dot. This you should keep it in mind. Now, you see, generally this for more accurate calculation, here you see a range is given, there we given a constant value of Kb value. These things more accurately we can find by using an exponential equation, which is given by Sigle and Miske, you can say. So, here generally they find a relationship between this diameter and this Kb value, you can see, like they use for a range of 2.79 millimeter to 51 millimeter range of what it is called size of the diameter of a cylindrical specimen, they use Kb equal to, you can say, 1.24, this equation actually 1.24 into d to the power minus 0.107. Now, if the thickness is 51 to 254, you can say, there they use this a linear equation, here you can see. Here one thing you should keep it in mind, for axial loading case, if the loading case is axial in nature, there generally this Kb value is considered as 1, what I am telling, understand. For axial loading case, this Kb value is considered as 1, this you should keep it in mind. Now, here you see, so this is, you can say, case of, you can say, reverse types of bending types of load. So, they are generally depending upon the size of the diameter, you see how the, you see this Kb value is varying. This is generally more accurate calculation, which is generally compared to this table, you can say data. Both the data you can use, no problem, what I am telling, understand. But this equation if you use, then for each and every diametral case you can use some differences of Kb value, what I am telling, understand. This you should keep it in mind. So, this is generally applicable for cylindrical cross section, this you should keep it in mind. For non-cylindrical cross section, generally what happens, this equation is not valid. For non-cylindrical cross section, like if the actual specimen have a section which is rectangular in nature, let this height is h and let us breadth is b. Then for this case generally what happens, there is required to use a what it is called equivalent diameter. Based on this equivalent diameter generally we need to find out what we need to find out the you can say kb value. This equivalent diameter first we need to calculate. After that, by using this equivalent diameter we use this exponential equation or this table data for kb calculation. This you should keep it in mind. Now, how to calculate this equivalent diameter, that now we need to know, that I am going to show. For calculating generally this equivalent diameter dE, that is generally called effective dimension or effective diameter dE. Generally here an approach is well established. That approach generally tell like that this effective dimension is obtained by equating the volume of material stress at and above 95% of maximum stress to the same volume in the rotating beam specimen. What does it mean? Generally let us, this is a rectangular cross section. In this rectangular cross section generally you know this bending stress, how it is looks like if this cross section is subjected to a bending moment mb like this, then what happens here, top side will be tensile in nature and it will be 0 at neutral axis and bottom side will be compressive in nature, correct. This you know. So, this is actually you can say sigma b maximum bending stress. So, here you see, and what we observe in case of circular cross section also, this bending stress, in case of rotating beam specimen we use a circular cylindrical cross section. Here also we observe what, that bending stress is maximum at outer fiber, that means here outer diameter, and it is gradually decrease and after that generally it will be compressive at bottom side. If it is subjected to what? If it is subject to hogging types of bending moment. That means, if the your specimen is bent like this due to bending moment mb, then what happens here, top fiber will be tensile and bottom fiber will be compressive in nature. So, it is generally you can say sigma b maximum. So, both rectangular as well as cylindrical types of cross section you can say this bending stress is varying, you can say linearly from neutral axis. This is actually you can say neutral axis NA I am writing, and it is linearly varying. Now, what it is consider here, this is very interesting thing. So, here this equivalent dimension or equivalent diameter you can say, it is generally expressed by the volume of material stress at and above 95% maximum stress. So, 95% maximum stress volume, which portion of volume will be stress? That means, you can say this is your 100% stress, which is maximum. Now, you see 95% stress will be this much volume. Let us here where the sigma b value is, you can say where the sigma b value is 95%. This you should keep it in mind. So, this mass cross section volume, generally here you see whatever the maximum stress, the volume of material subjected, that volume you need to consider, and that volume you need to equate with whatever the circular specimen is, the generally rotating beam specimen is there, that rotating beam specimen you can say here also you can say this is 100%, this is generally 100% maximum stress, whereas 95% maximum stress will be generally here. You see this mass of stress can be, let us consider 95% sigma b. So, you see as it is linearly varying, that is why you can say 100%, here you can say 100% sigma b, here the diameter will be how much? You can say outer diameter of this cylinder, and 95% specimen 95% bending stress will have a diameter which will be generally, as the bending stress is linearly varying, then we can consider 95% bending stress will be, you can say, where the diameter will be 0.95 of outer diameter. So, you see this is generally rotating beam specimen, this you can say diameter, where generally within this diameter range, that means 0.95 to D0, that diameter range you can say 95 to 100% maximum stress is varying. That volume you need to equate with, let us a rectangular section is there, in this rectangular section also at and above 95%, whatever the maximum stress generally volume it is subjected, that volume also here we need to consider. Now, let us consider this rectangular section and this cylindrical section have same length, what I am telling, understand. Then what happens here, due to this same length, once we go for calculating the volume, once you equate these things, what happens, this length will be cancelled out. So, that is why what happens, instead of considering this length terms, here directly you can consider how much cross sectional area is subjected to 95% maximum stress and it is above to 100% maximum stress, what I am telling, understand. So, that volume, that cross sectional area we will discuss. For rotating beam specimen generally or circular section specimen, you see this volume you can say is a ring volume. This ring volume have a outer diameter is D0 and in inner diameter is 0.95 D0. So, for this generally the cross sectional area A95 and its above, generally that is represented as A95. This you can calculate, you see, first of all the cross section area you can say of outer. So, outer diameter cross sectional area will be PD0 by 4. This is the outer cross sectional area, and what is the 0.95 cross sectional area, that will be 0.95 D0 into pi divided by 4, correct. So, this will give us this ring area, that ring area is which is you can consider a area above 95% stress. So, this cross sectional area here you see A95 that is represented pi D0 square by 4 and pi 0.95 D0 which is shown here you see. So, this you if you just do the calculation you will get a value which is 0.0766 D square, this you should keep it in mind. Now, let us consider this A95 we need to equate with what? This we need to equate with a, let us rectangular cross section or a square cross section is there. So, in case of a square cross section also you see this mass of cross sectional area we need to consider, where generally you can say this mass of, where generally you can say your bending stress here it will be maximum 100% bending stress, and here let us consider 95% bending stress. So, at and above 95% we need to consider. So, now you know. So, what is the value of this? You know these things very well. Generally here the total cross sectional area you can say of this rectangle is H into B, and above 95% you can say this we need to this mass area we need to subtract. So, this mass area we need to subtract, you can say that is actually what 0.95 into you can say H into B. If we just subtract these things, here you will get what 0.05 H into B. This is your B breadth and H is equal to height. So, this is the cross sectional area of this rectangle at and above 95% bending stress. Now, these things we need to equate with this rotating beam specimens, which is a circular cross section, which is a circular ring cross section you can say. This we need to equate with this rectangular cross section. So, this once we equate, that is equal to you can say 0.5 H into B. From here you can get a D value, that is called equivalent diameter of this non circular section. This you should keep it in mind. So, here you are getting, so D E equal to, you can write as a square root of 0.05 H B divided by 0.0766. This you should keep it in mind, which I have shown here. So, here you see the detailed things like you see a 95 of a 95, or you can say this, you can write a 0.95 sigma or 95% you can say. This equal to this area is 0.05 HB, which I have already told you. Now, what is DE equivalent? DE equivalent equal to this section area divided by rotating beam specimen cross sectional outer ring area, which is subjected to 95% bending stress and it is above. This you should keep it in mind. Now, here I have already told you, as here we consider the length of both the specimen is same. So, length will be cancel out. For different cross sectional area we can calculate which is subjected to 95% and it is above bending stress, and this value if we put here in this equation for different section, there we will get a DE value. This DE value generally we will use the previous slides equation or previous slide table data. Based on this table data you need to calculate what, you need to find out what is kV value. This you should keep it in mind. Okay. Now, these things generally I have written here very clearly. So, this you should keep it in mind. So, in one case here I have shown. So, for any types of other section, if it is a T section, if it is a L section, there generally how much area is subjected to what is called 95% stress and it is above, that you can easily find out. That section area you need to put in this equation. Let this is equation number 2, in this equation you need to put, and you can easily find out what is the DE value. Based on this DE value you need to use the previous slide exponential equation or the table data, and you need to find out what is kV value. This is very much important things you need to know.